In this video, we will look at some of the different ways that we use to represent molecules in terms of their various chemical formula. The particular atoms that make up a compound are represented by the compound's chemical formula. The chemical formula indicates the type and number of each element that is present in a compound, whether it be a molecular compound or an ionic compound. In the case of water, water is represented as H2O because the molecular compound of water has two hydrogen atoms that are bound to one oxygen atom. For carbon dioxide, it is represented as CO2 because there are two oxygen atoms that are bound to one carbon atom. In the case of an ionic compound like sodium chloride, where we can't really tell which atoms are bound to which, instead we represent it with the ratio of the atoms. So the chemical formula for sodium chloride is NaCl. The last example is carbon tetrachloride, which is represented as CCl4. This is a molecular compound in which one carbon atom is bound to 4 chlorine atoms. There are actually a variety of different chemical formulas that we can use depending on what we are trying to do and the level of information that we are trying to convey. Chemical formulas can generally be categorized into 3 different types. In our examples, we will be looking at hydrogen peroxide and octene. The reason one would use one of the different types of chemical formulas is based on the amount of information that is needed and what you are trying to do. The first type is an empirical formula, which is the simplest whole number ratio representation of the type and number of elements present in a molecule. In our example of hydrogen peroxide, this would be HO, and octene would be CH2. Essentially, the empirical formula tells you that for every hydrogen there is one oxygen, and in the case of hydrogen peroxide, and for octene, for every carbon there are 2 hydrogen. An important thing to note is that all ionic compounds are represented by their empirical formula, and that's because ionic compounds do not form molecular compounds. Right? When an electron is transferred to make your ionic compound, each one of your cations is interacting with all the anions around it, and so there is not a defined molecule. However, in the case of molecular compounds, there is a defined molecule, and you can tell what is bound to what. So for molecular compounds, we also have the molecular formula, which is the actual number of atoms of each element in a molecule of a compound. In our example of hydrogen peroxide, this would be H2O2. So in a molecule of hydrogen peroxide, there are 2 hydrogen atoms and 2 oxygen atoms. For octene, there are 8 carbons and 16 hydrogens. So the molecular formula for octene is C8H16. While molecular formulas do give us more information than the empirical formula, such as the exact number of each type of atom in the molecule, they don't really tell us how things are bound together. For example, this H2O2, we can't really, until we have developed our chemical intuition, know where the hydrogens are bound and where the oxygens are bound. And in the case of C8H16, there are a lot of different ways of arranging carbon and hydrogen atoms to come up with this ratio. So the molecular formula, while it does give more information than the empirical formula, does not necessarily allow us to know how everything is bound together. That is when we would move to the structural formula. The structural formula is a sketch or drawing of how the atoms in the molecule are bound to each other. So our structural formula for hydrogen peroxide would look like this. A hydrogen bound to an oxygen, bound to another oxygen, bound to a hydrogen. The lines here are representing our chemical bonds. So the structural formula for hydrogen peroxide is this, which, if we count up the hydrogens and oxygens, we get back our molecular formula. There are 2 hydrogens and 2 oxygens, so it would be H2O2, giving us back our molecular formula. The structural formula for octene, or one of the forms of octene, would be this. Note that this tells us where each hydrogen is bound. So we have at the end one carbon that is bound to 3 hydrogens. That carbon is bound to another carbon. That second carbon is bound to 2 carbons and 2 hydrogens. The next carbon along the chain is bound to 2 carbons, one via a double bond, as well as a single bond to a hydrogen, and so forth. So this here, as you will learn if you take organic chemistry, would be 3-octene, because the 3 tells us where the double bond is, right? But you can tell that the structural formula here gives us more information than what we had from the molecular formula. The structural formula tells us that there is a double bond, and it also tells us where the double bond is located. However, at times the structural formula can become cumbersome. So for example, if we were looking at this molecule here, the octene, as it is drawn out, and we did not know that it was octene, and I asked you how many hydrogens are there, you would actually have to count them up. Whereas if you have a molecular formula, the number of hydrogens is readily available. So determining the molecular mass of something via a structural formula takes a lot longer than determining the molecular mass of something given a molecular formula, as we will see in later videos. So to recap, the type of chemical formula that you're going to use will depend on how much is known about the compound and how much information you wish to communicate. In the case of a structural formula, this communicates the most amount of information. It conveys the type and actual number as well as the arrangement of the atoms in a molecule. It is a visual picture of the compound. However, at times it can be cumbersome to use depending on what you are trying to do. A molecular formula conveys the actual type and number of elemental atoms in the compound. It does not tell you how each of the atoms is bonded together, though by developing chemical intuition, in many cases you'll be able to deduce this from the chemical formula. However, not in all cases. Finally, we have the empirical formula, which communicates the least amount of information. It conveys the simplest whole number relationships of atoms to the other atoms in a molecule. Often, our experimental results when we are trying to determine the identity of a molecule will give us the empirical formula. It will often tell us the relative number of each of the different types of atoms, but it won't give us the molecular formula. This is the case of mass spectrometry as well as many other types of instrumental analysis. With the development of easily manufactured plastic and later computers, there became an additional method for representing molecules, and these are molecular models, which is a more accurate and complete way to specify a compound. Typically, these are represented in what is called a ball and stick molecular model, which represents atoms as balls and the chemical bonds as sticks. It will show how these two things, the balls and the sticks, are connected together reflect the molecule's shape. The balls typically have a color code to specify the various elements. Hydrogen is typically white, carbon is typically black, nitrogen is blue, oxygen is red, and then you have the other atoms being their own various colors. An interesting factoid is that the reason that oxygen is almost always represented as being red and nitrogen almost always as being blue is not that there is anything inherent to the element of oxygen being red and nitrogen being blue. Instead, the very first plastic model kit decided to have nitrogen be a blue color and oxygen be a red color, which is why all common pictorials of oxygen, whether it is in ball and stick form or a drawing, will paint oxygen as being red and nitrogen as being blue. Same thing with carbon as being black and hydrogen white. The coloration that is typically used for these model kits as well as drawings is all because of the very first model kit and the colors that were selected in those plastic molds. Molecules are not two-dimensional. They occupy three-dimensional space. So in comparing the value of information from our molecular formula to our structural formula, unless you know what you're looking at, the structural formula and the molecular formula don't really tell you what this looks like in three-dimensional space. However, a ball and stick and the most accurate space-filling model do show three-dimensionally. The ball and stick form is a little less accurate than the space-filling, but in losing a little bit of the accuracy of how much space the carbon atoms and hydrogen atoms actually take up, it does allow for an easier view of the different parts of the molecule when you're looking at them. You can see in our space filling model that it's a little bit hard to see all of this hydrogen in the back, and if you were to imagine the molecule rotating slightly, this back hydrogen could be completely obscured, whereas in the ball and stick, even if we rotate it a little bit, this hydrogen would still be in view. So we can have our space filling model in which the atoms fill the space between each other and more closely represent our best estimate of how a molecule might appear if scaled to the visible size. The hydrogens in our ball and stick don't actually take up this small space. They actually occupy a very large space, and they touch the carbon atom. A chemical bond is not done via these short little sticks. These are merely there to give us a way of representing the molecule. The more accurate form is the space-filling model. Let's now look at a couple examples to bring it all together. We could look at benzene, which has an empirical formula of CH. This ratio is what you would find from a lot of instrumentation like a mass spectrometer. It tells you that for every carbon there is a hydrogen, but it does not tell you how many carbons and how many hydrogens are in a molecule of benzene. Instead, we could look at our molecular formula of C6H6. However, the C6H6 does not tell us what the structure looks like, and often structure is important. So we can move to the structural formula, which looks like this. Again, we have 6 hydrogens and 6 carbons, although determining that we actually have to count. The structural formula does give us a good representation, but it doesn't, in some cases, give you a complete view of the three-dimensionality of the molecule. Instead, we can look at a ball and stick model, which in the case of benzene we can see is planar. The disadvantage of the ball and stick is it doesn't really completely indicate that the carbon atoms are touching. So we can move to the space-filled model so we can see how much area each one of the atoms is occupying. You have your hydrogens, which occupy a fairly large amount of space. The carbons are all touching, and so this is the most accurate representation. However, in many cases, it is not the easiest one to use. We could also have something like acetylene, which, like benzene, has a empirical formula of CH. However, acetylene is C2H2. This, again, does not tell us how things are bound together until you get good at it. We can look at the structural formula, which would look like this, which tells us how things are bound together. However, this doesn't really give us a good indication of the three-dimensionality of the structure. Instead, we can go to the ball and stick or the space-filled model. Our last couple examples are glucose and ammonia. Glucose has an empirical formula of CH2O. The molecular formula is a bit more complicated, C6H12O6. Going to the structural formula, this shows us how everything is bound together, but it doesn't really tell us the three-dimensional structure of it. The ball and stick model does give us a better indication of the three-dimensional structure, but again, it doesn't tell us how close everything is together. For that, we need the space-filling model. And finally, ammonia, in which the empirical formula is the same as the molecular formula. This can be the case. The molecular formula is NH3, which is the same as the empirical formula. There's only 1 nitrogen and 3 hydrogens to this molecule, and that is the simplest whole number ratio. The structural formula looks like this. Ball and stick is here, and then space filling, we can see what the molecule actually looks like three-dimensionally.